Hey guys, today I am going to be talking about a certain constant in physics and chemistry. I'm going to be talking about Avogadro's constant, more specifically, how the constant was determined. First off, what is Avogadro constant? The official definition for Avogadro's constant is the number of atoms in a mole of something. A mole of a substance will have the same number of atoms or molecules as there are atoms in 12 grams of carbon-12, which is the most abundant isotope of carbon. Now, the number is also the number of molecules in 2 grams of hydrogen gas, which has a relative atomic mass of 2, and it's also the same number of atoms in 236 grams of uranium-236, if you could kind of see it trending. So as you can guess, Avogadro's constant is quite a massive number. It's about 6.022 times 10 to the 23. It's a massive number, and let me just tell you how big it is. Suppose I have a mole of rubber ball in a massive pit. That's going to be 6.022 times 10 to the 23 balls. Now, I'll get every human on Earth right now, that's about 7.4 times 10 to 9 people, to pick out the balls at a rate of 1 ball per second. How long would that take? The pit would be empty in about 2.6 million years. How long ago our first ancestors, Homo habilis, lived? So obviously, this is a very big number, which makes it a bit hard to find if you just want to individually count the number of atoms in 12 grams of carbon-12. That's not really practical. We need other methods of determining Avogadro's constant. Now, the constant was named after an Italian scientist, Amedeo Avogadro, who himself didn't come up with a numerical value for the constant. This was Jean Perrin's idea to name the actual constant after Avogadro. Avogadro's big discovery, though, was finding that equal volumes of gas under the same temperature and pressure will have the same number of molecules in it regardless of what type of gas it is, which itself is quite cool. Now, the first scientist to do anything with this issue was a guy called Johann Magnenus in 1646. Now, his method of finding the number of atoms in a mole involved burning some incense in a room and then using the time until he smelled the incense, and then finding the size of the room, and then using the size of his nose cavity to try to work out what the mole is. And using this method, the Avogadro's constant was calculated to be only about 1 order of magnitude of the actual value, which is really impressive considering that it was a period of time where the elements were the same ones that we found in Captain Planet. You know, Earth, Wind, Fire and Air. And the first proper estimate of Avogadro's constant was by a German scientist called Loschmidt in 1865. In his paper, he was able to determine the volumes and cross-sections of an atom using the kinetic theory of gases developed by a scientist called Daniel Bernoulli 130 years earlier. Now, Loschmidt was able to determine d, the diameter of the atom, to be about 1 nanometer. Well, determining the value for d was done by using some liquid air, which contains nitrogen and oxygen, whose particles will touch because they're in liquid, and so their volumes could be found a lot easier. And assuming that when you heat the air up, this liquid will just turn into gas, and that gas will have the same volume as the liquid originally. Now, Loschmidt was also able to find something else called the free path of particles, or basically the mean value of the distances particles will move before colliding in with another air particle. And this involved some known values, as you can see here. It involves d, which is something that Loschmidt was able to find earlier. It also involves n0, which is Loschmidt's constant, or the number of molecules in 1 cubic meter of an ideal gas under standard temperature and pressure, which is 273 kelvins and 100,000 pascals. And by plugging all the known values into the equation and then solving for n0, Loschmidt's constant was found to be at about 1.8 times 10 to the 24. Now, using this value of Loschmidt's number and this very equation that links the two constants, Loschmidt's number and Avogadro's constant together, we can find the Avogadro's constant. R is the ideal gas constant, which is about 8.314. We already knew that by then. While the pressure and temperature used is also known as it is in standard condition, as I mentioned earlier. With Loschmidt's method, Avogadro's constant is found to come to about 4.1 times 10 to the 22, which is still quite accurate. It's also worth mentioning a bit here that in places like Germany, Loschmidt's constant can be used to mean both the number found by Loschmidt or to mean Avogadro's constant, which is what we're talking about here. It's also why in some places you'll see the Avogadro's constant being abbreviated by the letter L rather than Na. And then after that came Brownian motion. This was in fact discovered by a botanist called Robert Brown in 1827 when he wanted to study some pollens by placing them on water. But when he looked through the microscopes, he found that the pollen was moving randomly. And because he was a botanist, he wasn't really able to describe why that was. No insults to botanists out there, they're good people. It was only about a century later that both Einstein and another scientist called Semoloshowski, well, I probably bottled the pronunciation of, started to understand more about Brownian motion. They found that these pollens were moving due to their random collisions with the molecules, which was also moving randomly. So how is this related to finding Avogadro's constant? Well, basically, using Brownian motion, Einstein was able to come up with some kind of relationship which involves something called the Boltzmann constant. The Boltzmann constant is a constant that links the temperature to the amount of energy in the particle with the equation energy equals 3/2 times Boltzmann constant times temperature in kelvins. He stated that the diffusion coefficient of fluids, which is just a constant showing the amounts of motion, equals to the mean squared displacement of particles divided by 6 times time. The mean squared displacement of particles is basically just the average of the squares of each movement of the Brownian particle. Now, Einstein also found that the diffusion coefficient equals to the absolute temperature in kelvins times the Boltzmann constant divided by 6 pi times the viscosity of the fluid times the radius of the Brownian particle. Now, we don't know what the value of the Boltzmann constant is. However, with all the other values in the equation Einstein used were able to be measured or is already known, we could find this mysterious Boltzmann constant. And to find Avogadro's constant from that, you can divide the ideal gas constant, which is still 8.34, by the Boltzmann constant. And it was a guy called Jean Perrine, remember him, who was able to experimentally test out this very idea. He was able to find the mean squared displacement of the particles in Brownian motion, and with that, with a bit of maths, found Boltzmann's constant and then Avogadro's constant to be around 7.05 times 10 to the 23, which is not far off at all. Now, the next method involved two other constants, Faraday's constant and the elementary charge. Both of these constants were discovered at different times by different scientists. The Faraday's constant is the charge on 1 mole of electron, which was discovered by, you've guessed it, Michael Faraday. Whereas the elementary charge is the charge on a single electron, which was found by the American physicist Robert Millikan. If we know the charge of 1 mole of electron and the charge of a single electron, dividing the two would just give you the number of the electrons in a mole of electron, which is the Avogadro's constant. Simple mathematics. Now, Faraday's constant was discovered first, and it came from Faraday's law of electrolysis, discovered in 1834. Electrolysis is when we run DC current through some substance which causes some reaction to happen which would have not happened otherwise under normal conditions. For example, if I were to stick 2 copper electrodes into some copper solution and run some DC through it, on the positive electrode, the copper atom in the actual electrode would be oxidized or have the electrons taken away from them, making copper 2+ ions, and these ions will enter the solution, causing the positive electrode to be smaller. Whereas on the negative electrode, the positive copper ion in the electrolyte gets attracted to the electrode because of different charges. They're reduced or being given electrons and form copper atoms which are deposited on the electrodes, making the electrode bigger. And well, the electron made in the positive electrode would move through the external circuit and then to the negative electrode to be given away to the copper 2+ ions. Now, because there is a movement of electron in the external circuit, that means there must be a current which is being provided from the external cell. Now, there is two laws of electrolysis. The first law is unimportant to our discussion, but the second law is what we are concerned with. It states that if you apply equal current to different electrolytes or elements, the mass of the product produced will be proportional to the relative mass of the substance. Now let's go back to our example of electrolysis from earlier. I'll only deal with one of the electrodes on the half equations on the negative electrode. Now the power of balanced chemicals equations tell me that for every 2 electrons that reacts, there will be 1 copper atom forming. So to form a mole of copper on the electrode, you'll need 2 moles of electrons. Now you can weigh the electrode before and after the reaction and find the difference of copper being produced. You can find how many moles of copper is extra, and double of that number will give how many moles of electrons is involved in the reaction. And the charge added to the electrode can also be found, because we know that charge equals to the current through the wire times the time or how long that current is running for. So with some chemical proportions in maths, the charge of 1 mole of electron could be found, and this value, the charge in 1 mole of electron, Faraday's constant, is found to come out to about 9.65 times 10 to the 4 coulombs. And now, Robert Millikan. He did an experiment called the oil drop experiment to find the charge on a single electron. You see, these oil drops have some extra electrons on them, so their charge isn't going to be quite 0. If you put these oil drops between 2 electric plates, 2 charged electric plates, it would get attracted by one of the plates because of its charge. So what Millikan did was he rested an oil drop between 2 charged electric plates. And then he turned off the electric plate so there was no charge anymore and let that oil drop until it reaches terminal velocity. And then he did some maths with it. So first, Millikan had to let the oil drop stay stationary. And because the oil drop is stationary, the force is acting up on it and the force acting down on it must balance each other out, so there's no acceleration. That's Newton's first law. Now the force involved here was going to be the force due to electric plates, which would equal to the charge on the oil drop times the potential difference between 2 plates divided by the distance between the 2 plates. And the weight of the actual oil drop, which equals to the drop's mass times the gravitational field strength, which on Earth is 9.81 meters per second squared. And these 2 forces must equal to each other. Now here Millikan could just rearrange the equation to find the charge on the oil drop. Note that this is the charge on the oil drop and not the charge of the individual electron just yet. Here we know that the potential difference and distance between the 2 plates, because we kind of set that, and we know the gravitational field strength on Earth, as I mentioned earlier. The mass of the oil drop, however, we don't know. So we'll have to do something else to it. And this is when Millikan turns off his electric field and allows the oil drop to fall until it reaches terminal velocity, or when it doesn't accelerate anymore. At this point, all the forces acting upon the oil drop will be equal again. The weight is still acting down on the oil drop, but acting upwards instead is air resistance, the first time you'll ever be considering it in physics. The force due to air resistance follows Stokes' law. So the force would equal to 6 pi times the viscosity of air times the radius of the oil drop times the velocity the oil drop is falling at, which could just simply be measured. And this second bit of the experiment is needed because the oil drop's mass cannot be measured directly. It's a bit too small to use a balance or anything with. So by also considering the density of the oil drop and assuming that the oil drop is around sphere, you can use the equation V equals to 4/3 pi r cubed to this. You are able to find the radius of the oil drop, which then could be used to find the mass of the oil drop and then the charge of it. Now what Millikan found was that the charge on the oil drop will always be a multiple of a certain number. This certain number is the charge of electron, which at the time was found to be 1.59 times 10 to the minus 19. The reason that it's always going to be a multiple of this certain number is because you can't have half of electrons, so it's always going to be a full integer of number of electrons times the charge of the electron, which is being responsible for that overall charge of the oil drop. Or basically, whatever the charge of the oil drop is divided by 1.59 times 10 to the minus 19 will give you the number of electrons that's responsible, that's extra in that oil drop. And that's always going to be an integer. So from there, he was able to draw the conclusion that a charge of electron must be 1.59 times 10 to the minus 19. So if you were to divide Faraday's constant, which we found earlier, by electrolysis, by the elementary charge we found by Millikan's oil drop experiment, you found that Avogadro's constant will come to 6.06 times 10 to the 23, which is getting even more accurate now. And then came Max Planck and the black body radiation. The black body radiation is some object which would absorb all the radiation that hits and then re-radiates that energy back out again. The reason that the black body re-radiates the energy back out is because of the second law of thermodynamics, that energy cannot travel from a cooler to a hotter object unless work is done. So now when you send radiation to the black body, it gets absorbed and it heats up the black body. And then at the point when the temperature of the surrounding equals to the temperature of the black body, any more energy absorbed by the body will cause it to become even hotter, and it become hotter than the surroundings. And so energy, because the body is already hotter, will radiate the energy out, that extra energy out, to go back to the thermal equilibrium where the temperature of the body and the surrounding is the same. Now, Avogadro's constant could be found using the help of Planck's law, which is a law that describes the amount of electromagnetic radiation emitted from the black body when both the black body and the surrounding is at a certain temperature. Now, the equation is as following. Now, it doesn't really matter too much for us, but those interested, the spectral radiance, or basically the amount of energy given off by the body, depends on the frequency of the electromagnetic wave and on the temperature of the system and the body, which would be the same at equilibrium. And the rest of the terms are all just constants. Now, I apologize for not deriving this formula. It's a bit beyond me. For anyone interested, this equation was an improvement of Rayleigh-Jean's law, where the energy of the particle back then wasn't this, but was considered to be the Boltzmann constant multiplied by the temperature. This, however, results in a UV catastrophe, where the high frequency UV waves would cause intensity so high that it would kill you. But in reality, the experiment doesn't show this, and this is reflected better in Planck's law. Now, from this equation, Planck's law, we can get another equation describing the energy density per unit volume per unit frequency. Experiments allowed us to work out Planck's constant and therefore the Boltzmann constant, which, using the same equation from above, Boltzmann constant divided by the ideal gas constant, will give you Avogadro's constant, which, using this method, comes around to be 6.175 times 10 to the 23, or at least at the time of this discovery. And then came Ernest Rutherford and Boltwood in 1911. Their method involved counting the number of alpha particles produced by some sample of radium. Alpha particles are simply just nuclei of helium atoms without the electrons whizzing around it. So what they did was they took some radium salt and placed them into a platinum capsule and sealed it very well. And after about 83 days, the seal is broken and the volume of helium gas produced is found. This value was found to be about 6.58 millimeters cubed. Now, the second sample is prepared, and instead the seal is broken 132 days later, and the volume of helium gas produced this time was found to be about 10.38 millimeters cubed. Now, from the two sets of information, they were able to find the amount of helium gas produced per day in both of the samples. It came out to be 2.9 times 10 to the minus 2 and 2.3 times 10 to the minus 2 millimeter cubes per day for each of the sample, which showed consistent results. Now, the average of these two values of helium gas produced per day could be used, and they found that the amount of helium gas produced per gram of radium per day equal to about 0.107 millimeters cubed per gram of radium per day at normal temperature and pressure, which is 20 degrees Celsius and 1 atmospheric pressure. And using a bit more maths here, you can find that this is equal to 5.55 moles of helium being produced per gram of radium per second. Now, a few years earlier, Rutherford with another guy called Geiger found that a gram of radium would emit 3.4 times 10 to the 10 alpha particles per second using some kind of Geiger tube machine thingy. So knowing the number of moles of alpha particles and the actual number of alpha particles being emitted per second, they were able to work out Avogadro's constant to be around 6.1 times 10 to the 23. Now, this actual value, 6.1 times 10 to the 23, wasn't something that was actually stated in Rutherford's experiment. It was something that you can find as a result of his experiment. It was in 1928 when another guy called Wertenstein came along and improved on Rutherford's method and was able to get an even more accurate value of Avogadro's constant at 6.16 times 10 to the 23. And then came the year 1930, the year where scientists started to use X-rays to help determining Avogadro's constant. This technology was already being in use since 1912 to determine spacing in lattices, but it was only 18 years later that it was used to find the mysterious constant scientists were after. This was because we didn't know the wavelength of X-ray waves at the beginning. It was only in 1928 when a guy called Backlund was able to partially solve this issue by determining the wavelength of K alpha doublets. Now, for quick explanation, X-rays are electromagnetic radiation, which means they are basically photons that are moving at the speed of light. But how are these photons of X-ray made? Well, first, in an X-ray machine, there will be a cathode which is emitting off high-speed electrons, which are shooting towards some kind of an anode. And when these electrons gets to the anode and interferes with the atoms in the anode, it can do two things. The electron itself could come in and then interfere with the atoms in the anode, the nucleus of the atom in the anode, and this would cause them to start to break and lose its kinetic energy. And because of law of conservation of energy, this kinetic energy loss must go somewhere. And the energy is not just lost, it's lost in a form of photons, because the electron then emits some kind of photon out, which is the energy it loses. So it breaks, and then it radiates off some energy, and this is what we call breaking radiation, or in more fancy terms, Bremsstrahlung, which is a German word I probably bottled the pronunciation of. Alternatively, the electrons could come in and then knock off an electron that is in the atom of the anode, and then causing a little gap in the energy level. This then will result in a higher energy electron of the same atom to get de-excited into the lower level, and because it goes from a higher energy level, it contains higher energy, and then goes to a lower energy, it loses its own energy, again in terms of photons. And these photons are what the X-rays are, because X-rays are just basically high moving photons. K alpha emissions are caused from photons which are emitted when electrons move from the 2p orbital of an atom to the 1s, or the lowest energy level. Moving down the energy level means they lose energy, they get de-excited, which causes them to emit a high frequency photon, which are the X-rays. The reason that there is a doublet is because there could be two possible energy levels and different photon energies being produced, because there are two different spins of the electrons with two different orbital momentum in the 2p orbitals, which they can de-excite from, which causes them to have two slightly different energies when they get de-excited. Now, to determine Avogadro's constant, we divide the mass of 1 mole of a substance, or the molar mass, by the mass of an individual molecule, or the molecular mass. The mass of an individual molecule equals to the density of the substance times the molecular volume. The volume can be found from finding the volume of a bunch of atoms connected in what we call unit cells divided by the number of atoms in those unit cells. Now the X-rays come in because it's used to determine the spacing of the lattice, which then could be used to find the volume of the unit cells, and then, as I mentioned earlier, to find Avogadro's constant. Now the reason X-rays can be used in calculations of Avogadro's constant is because X-rays will scatter in predictable ways when passing through crystal lattices of silicon, for example, and then these scattering allows scientists to determine the lengths between the atoms of the crystal and the lattice, and then hence the volume of the lattice, and then eventually the Avogadro's constant. Now, early X-ray works involved the use of calcite crystals, but eventually germanium and silicon were used instead. This was because calcite crystals showed varied densities between each samples. Now, attempts from both a guy called Deslates in 1980 and NIST in 1998 used silicon samples and agreed upon Avogadro's constant to 4 significant figures, 6.022 times 10 to the 23. And then came Avogadro Project, which was set up to find Avogadro's constant with a relative uncertainty of 2 times 10 to the minus 8, which is tiny, and also to partially help redefine the kilogram, to not, rather than use a kilogram prototype, which is literally just a weight of an exact kilogram, which could just change at any time according to the environment and by other stuff, which I'm not going to really go into details at for this video. Well, this was a collaborative project between many countries and involved a very round spherical ball of almost pure silicon 28. Check Veritasium's video on that really round sphere. Using this method, we'll find what Planck's constant is, and from that we're not only able to redefine the kilogram, but also get a more accurate value for Avogadro's constant, which is related to Planck's constant by this equation. And now the latest value of Avogadro's constant found in 2015 is to the nearest 9 significant figures, 6.0221407 times 10 to the 23, with an uncertainty of 2 times 10 to the minus 8. And nowadays, with these new methods of finding Avogadro's constant, which is really accurate, we're able to also redefine the previous mentioned Loschmidt's constant and Faraday's constant, which used to define Avogadro's constant, but now becomes the other way around. The Avogadro's constant define what the Faraday's constant is, and define what Loschmidt's number is. Avogadro's constant, as you can see, is a very important concept in physics and chemistry, and has a long history behind it. And yeah, that's about all I have to say on Avogadro's constant and how it's discovered. Thank you very much for joining in, and I'll see you again soon. Goodbye.